Good evening, everyone. My name is Amit. Am I audible?
Yes, sir.
Yes, sir.
Okay. Um, this is for Basic Electronics course NOC 23 EE62. You must be aware about it.
How can I?
This will be our first problem solving session. We intend to conduct 12 such sessions. I'm going to take up some problems which have been asked some previous years, not current year's assignments, because that won't solve the purpose. You won't learn much. So we're going to solve some problems which are directly linked to your lectures that you have gone through. So for instance, today we are going to solve problems which are related to week 1 content, and we are just not going to solve the problems. I'll also frequently pause if you have doubts related to the videos of this week. You're welcome, you're more than welcome to stop me anytime and ask, and that's the whole point of this exercise that we are doing here. Right. Just for starters, I'll introduce myself first. Just hold on a second. Um, hopefully you are able to see my screen. Can someone please confirm?
Yes, sir.
Okay. As I told you, my name is Amit. I'm a fourth year research scholar at Indian Institute of Science, Bengaluru. Currently, I'm working on devices called on a semiconductor material named gallium nitride. So this is my work that I've been doing. As I told you, I'm in PhD. I have been a teaching assistant for various courses in physical format, as well as on the online format, at least for the past 2 years. And so these are my contact details. If you want, if you are I'll also write them in the chat box. This is my email ID, that my institute email ID, amitbansal@iic.ac.in. However, I will recommend you to email me for any doubts or comments or discussions on the bottom email ID, that is learnwithamitbansal@gmail.com. Also, which might be of relevance to quite a few of you, there is a YouTube channel that I have with the same name, Learn with Amit Bansal. I'll share that right now. Just hold on a second. um, yeah, are you able to see the YouTube page? Just confirm. Yes, no? Am I- are you able to see the YouTube page?
Yes, sir.
Yes.
Okay.
Yes,
So this
sir.
is my YouTube page. So whatever sessions we conduct here, so every week we will conduct one session, and I'll update the record and I'll upload the recording of that particular session on this YouTube channel. So in case you have missed or you want to revisit something, you are more than welcome to visit this channel. I'll share this the link for this channel again in the chat box. So that's about me. Now, final thing that I want to talk about is
Sir, I have a doubt.
yeah, please go ahead.
This week sessions assignment, what is the time limit for that?
So talking about the assignments that you are required to submit.
Week 1.
Okay, so
Yes, sir.
I was going to open that page. It's good that you asked. So just give me a couple of minutes and we'll talk about that. Just
Sure,
hold
sir.
on a second. Let me, yeah, okay. So are you able to see the screen? The NPTEL, the Swayam portal screen?
Yes, sir.
Okay. Just 1 second. Yeah. So on this screen, this is the announcement that you have. So there are many tabs on the top. For instance, I have currently opened the announcements tab, in which you can see that there's an announcement that on 4th of February there will be a live session, which we are currently going through. Now if you go here, so on the left side you have a menu, so to say, an index, so to speak. So under week 1, if you see quiz week 1 assignment 1. Okay, I clicked on that, so the link is opening. Just let's wait for a minute. Yeah, so now you can say that you can see on the top right there's a due date. Can you see that the due date is 8th of February 2023, 23:59 IST? So that's midnight of between 8th and 9th February. Are you able to see that?
Yes, sir.
So
Yes, sir.
does that answer your question?
Yes, sir.
Okay, so this is the web, this is from where, this is your contact point. So there are other things also. For instance, you can ask a question, and there are many other things on this portal, which I recommend you to just browse through the options, and that will be very beneficial. So on your screen, you must be able to see a discussion forum, right? I hope that's visible to you. So on this discussion forum, you can ask questions with your fellow learners. And for instance, I am also added to that, and I assume the other TAs, and they keep on reviewing this so as to get an idea that what are the common doubts, so that they can be discussed in live interactions, and any other opportunity. So this is the platform that the NPT, this is included in the NPTEL. So this is not something from my side. What I am going to tell you now, so I am going to share my email ID. I'm going to share my email ID, with which you can, I highly encourage you to use the discussion forum, because by using that, many people will get to learn. The fellow learners can solve your doubts, not just the person sitting who are supposed to teach you, right? So this is my so on your screens, I've just shared my email ID in the chat. And I'll also share the link to my YouTube channel, because in case you miss a session, or you don't have time for whatever reasons, you want to revisit, so you can visit this YouTube channel as per your convenience. Okay, so that's about the contact details. People are still joining, so I'll wait for a maybe a couple of more minutes, and then we'll start solving the problems. So as you're aware, this is a 2-hour session. Usually it's designed that I try to solve the problems in maybe 1.5 hours. So I'll try to pause a bit, ask take questions, and I'll also include the concepts which are discussed in the lecture, a brief summary of it in the question itself, so that it gets revised, it gets revisited over and over again, and gets ingrained in your minds. Right, now before I go ahead, I need to ask a couple of questions. Currently I can see there are as many as 37 people. Okay, I'll exclude myself. So there are around 35 people in this Google Meet right now. So can you confirm that, which, if you are in first question is whether all of you are from electronics background? Anyone who's not from electronics background, please respond in the chat box. Okay, one, or raise your hand. Yeah, that's better. Raise your hand if anyone who's not from electronics background. Okay, one CSE. So I can see, just hold on a second. Just keep your hands raised. So there are 3 people. Okay, the 3 people not from electronics background. Okay, the follow-up question to these 3, sorry, now there are 5 hands. Okay, so the question to each one of you, can you please reply in your chat box in which year of your corresponding degree course you are in? Because if you are first or second year, then I'll try to build up more on concepts. Okay, first response is first year. That's good. Just keep responding. I'm reading. Second year. All right. 2 first years, second year, third year. Okay, so for third year, I can just since there are first and second year people, so first year. Okay, fine, that answers my question. Thank you for your responses. First and second year, quite a few first and second years. All right, now you can lower your hands now. Thank you for your responses. Please lower your hands, because otherwise it will create problems for the next question that I'm going to ask. All right, Santosh, Induja, please lower your hand. Okay, my next question is directed to the people who are from the electronics background. In which year are you people, first or second year? I know this is an undergraduate level course, but I need to tailor my content. I need to, according to the level of students they are in. All right, so just first and second year people raise their hands. That will give me an idea. Whoever in first and second year, just chat box will get cluttered. Just raise your hands. I'll count the number of hands raised. First and second year electronics background students. All right, so there are 14 hands raised. So I assume the rest, around let's say 25 to 30 people, are third and fourth year, right? Okay. Right. Yeah. Thank you for responses. I think I get the idea of the audience now. Thank you for your time. Please lower your hands. Thank you. in case you have any other queries regarding the way to conduct, I'll just introduce how will I conduct the sessions. As I told you, I have some questions which I have. We are going to discuss that in class, and these questions will not be in isolation. There will be the content that is there will be closely associated with what you have read, which what you have seen in the videos, and also closely related to the upcoming assignment that you have on, in this case, 8th of February. So they will be closely related. Secondly, I'll revisit some concepts, and thirdly, and this is the most important thing, I highly encourage you to use the discussion forum, or if you're not, or if you don't feel comfortable posting in public, I've given my email ID to you people. You can, if you, for some specific doubts, you can please email me that, so that I'll try to include in the next session. So as I told you, I've conducted this session quite a few number of times. So some people, they tend to like ask a lot of doubts, and they don't feel comfortable in on a public forum. So that's that. And okay, so there are a few, just give me a minute, there are a couple of questions. Secret tips to become IIT, and I don't think this is relevant to this forum, but email me, maybe we can talk on the email address. Second question is, what about
Excuse me, sir.
simulation stuff sir teach, is it exam relevant or just for intuition? So the simulation is for this course as well as for other courses. First of all, in general, simulation just helps you for a better understanding. You're just not solving problems on paper and pen. When you simulate them, you can introduce some non-idealities also, and that's good for a holistic understanding, and just for a basic thing. Okay, one more thing, for simulation related questions, please direct it to the TAs of the course which you have been allocated. I'll be mostly dealing with your problems, problem statements, like assignment questions, and in between some conceptual doubts regarding simulation, and simulation, and in particular, and other content related things. I request you to please, there is a list of TAs for this specific course. You please refer to them. So, or even better, just post on the discussion forum, because TAs are required to frequently check the discussion forum. So any doubts you have, you must post, because like at least 2 people have asked about simulation. So you ask over there about simulation. If there is any question, okay, there are few raised hands. So simulation related questions, unfortunately I won't be able to answer. Yes, Santosh, go ahead. Okay, it's better if you type. There might be some connectivity problems. I'm not able to hear anyone. Can just please type your queries. Santosh, Arun, Birudev, Nachiyar, please type your queries or comments or whatever they are. I'll respond. Okay, so I don't see any chat.
Sir, actually, I have a doubt.
Yeah.
Sorry to interrupt, sir. Actually, as we are having our internals from Monday, so is this class also going to be uploaded in your channel?
Yes, so this interaction session where we solve the problems is going to be uploaded on my channel. So most likely, today is Saturday, so by tomorrow I'll upload it. So you just visit the link, the channel name that I had shared. You can just visit the video.
Sure, sir. Because because of the examinations, our friends and some of my friends are unable to join.
No, that's fine.
So that's the reason I asked the question.
That's the whole point, that NPTEL had asked us to record these videos, these interactions, and then upload them on the YouTube, because
Thank you, sir.
for whatever reasons, people may not be able to join. Right. So okay. So I guess there are no comments. Okay. So that's for that. So I'll cater. I have an idea about the audience over here. So now we'll quickly jump in to solve the problems. Let me share my my slides. All right. Can you confirm that you can see the screen? Can someone?
Yes, sir.
Okay. Good.
Yes.
So now we'll just jump into solving the problems. Okay, basic electronics, week 1, February 4. My name is Amit, and this is the first problem that we have on hand. So I'll introduce the problem, and we'll pause for a bit, and then we'll try to solve. We'll try to see the approaches, which are closely linked, as I told you, with in the lecture that we had seen on the Swayam portal, right? So the question asks, in the circuit shown in the figure, what is the Thevenin voltage as seen from AB? So essentially, we need to find the Thevenin voltage. So VTH is the thing that is required, and VThevenin when viewed from here. All right. Four options have been given, and we'll try to find the correct option, right? And this is the circuit that has been just redrawn. Just I've omitted the options. Just hold on a second. Right. Okay. I'll reshare my email ID and the YouTube channel link. I'll again share it in the middle of the session and at the last also, so there's no need to worry. Okay, getting back to the problem. So we are required to find the VThevenin. Okay, can someone just tell me what's the concept of a Thevenin? Okay, let me just introduce. So you see, this is a very complex circuit. There's a voltage source here. There is a current source here, and there are few actually 5 resistors, right? And usually, what we want is that we want it to convert it. We want it to convert it into. We want it to be converted into a black box. We don't care what's inside, how complex the circuit is. We only care about what is being outputted at A and B. So we call it R Thevenin, and the correspondingly voltage source to be V Thevenin. So you can see all this stuff, VS, IS, R1, R2, R3, R4, R5 have been clubbed into VTH and RTH. This is the equivalent. So how do we ensure this is the equivalent? So that's the way we are going to draw. We are going to draw this circuit, and we are going to arrive at V Thevenin and R Thevenin. Can someone tell me how do we calculate V Thevenin? How do we calculate Thevenin voltage for any given circuit?
I think we have to use source transformation.
Okay, that's one approach. I'm going to that. Yeah.
Yeah, we may short the like voltage source and open the current source.
Okay. So
Like
okay.
we
So very good. Go ahead. Any other suggestions? These are very two prominent suggestions. In fact, the two most commonmost approaches have been suggested to me already. Any other approach? Because the more we talk, the more different approaches will arise. Okay, so the first person talked about that we can convert these voltage source to current source and vice versa, and the second approach what was talking about, I hope, was the superposition, right? And coincidentally, these are the two topics that were discussed in class. For superposition, we are not going to solve this problem using superposition, but we will see superposition in this session. What we are going to do is that, so I told you that, just give me a minute. Yeah. So I told you this is an equivalent circuit of this. However, there is another equivalent circuit, and it looks something like this. This is the voltage equivalent, and this is the current equivalent. Again, this is the black box. We don't care what's inside. We only care what's coming out from A and B. This one is usually referred to as a Thevenin circuit, Thevenin equivalent, V Thevenin, R Thevenin, and the correspondingly ones are a Norton. So this becomes IN, and this becomes RN. So how are they related? RTH equal to RN, and V equal to IR. So VTH equal to IN times RN. So if you find this or you find this, it doesn't matter. They are the electrically they are the same, and this is of importance. This means we can, as per our convenience, now what we can do, we can switch between one and the other, and that's what was suggested. So what I'll do is that, so just consider only this part, the VS and R1, right? So I'm going to consider only this now, only this part of the circuit, right? Only this part. Now I know this is in this configuration, VTH RTH. You can see that VS and R1 are in this configuration. I can simply convert to this configuration. So how do I do that? I can say, now this highlighted part can be written as, alternatively can be written as, current source, this remains the same, and then we will hook up IS, R2, R3, R4, and finally we have R5. So this is A and this is B. I have done nothing except replace them. So I told you RTH equal to Rn. So this remains R1 itself. The value remains R1. However, this will change. This will become, I told you, VTH equal to IN times Rn. So this value will become 5 volts over 5K. This is coming out to be 1 milliamps. So this current source will now be a 1 milliamps. Coincidentally, this one is also of 1 milliamps. Now, what do? Now you can clearly see this 1 milliamps and 1 milliamps are in parallel. So what I am going to do, I am going to club them, and we can also see R1 and R2 are in parallel. So firstly, I am going to club I. So this is for the next step. For the next step, what I am going to do is I'm going to club. Okay, yeah, there are 2 hands raised. Santosh. Okay, I am not able to hear anything. Birudev. Please write, if sometimes the voice doesn't come, you can unmute yourself, check that. If not, just type in the chat box, I'll read it. Just type in the chat box, I'll get back to it. Right, so I1 and I2 are, since this one, this current source and this current source are in parallel, so I can simply combine them and my new current source will become 2 milliamps, 1 plus 1. Also, R1 and R2, you can see they are in parallel, right? So R1 is 5K and R2 is 2.2K. So I'm going to call it, let's say, R12. R3 will remain the same. This part of the circuit will remain the same from here onwards, because we have converted only, we have simplified only this left half of the circuit. So R3 will remain the same, so will R4, and R5 will also be the same, and A and B points continue as before. So let's calculate R12. So R12 is nothing but R1 parallel R2 over R1 plus R2. Let me get my calculator. So this will be 5 times 2.2 divided by 7.2. This is coming out to be 1.53K. Okay. So we have all the currents, R3, R4 and 5, by the way, are already known. Okay. So now what we'll do is we'll go ahead and simplify this even further. How do I do that? You can see that if I convert it back to the voltage form, this format, then the resistance that will come here will simply add up with R3, and that will simplify the circuit again. So what I'm going to do, let me redraw this circuit first. Okay. So we had 2 milliamps, 1.53K, and I3 onwards it remained the same. So this was 1.5K, 4.7K and 3.3K, A and B, right? So I told you, let's convert this back to the voltage form. So if I convert it back to voltage form, and we know that VTH equal to RTH times IN, the Norton. So Norton here is 2 milliamps, RTH is 1.53K, so VTH will come out to be 3.06 volts. So let me draw that now. So this will become 3.06 volts, and this is 1.53K and 1.5K. Note that I have only considered only this part. Please note that. This is what I am drawing over here. Alright, the bottom doesn't change. This is 4.7 and this is again 3.3K, and A and B remain the same, right? So now you can see, so now what I'm going to do, now again I can see that these two are in conjunction. So now I'll take the purple region, right, and I'll draw the Thevenin equivalent for that. So what's going to happen, I only care about this black box. So again this is fairly simple. So this will remain 3.06 volts, and 1.5 and 1.5 will combine to give me 3.03 kilo ohms. Rest of the circuit remains the same. This is 4.7K and this will be 3.3K, and this is again A and B, right? So we have come thus far. Santosh, Birudev, Gautam, anyone? Please respond. Please ask. Your hands are raised. I'm not able to hear anything. Just please type in chat box if you're not able to. Your voice is not getting to me. Please type in the chat box. Okay.
Clear, sir.
Okay. So now moving forward, now what I'll do, again, I'll convert this part into Norton equivalent. So I'll just, for the sake of simplicity, assume them to be 3 and 3 because the calculation might get a bit tricky. So 3 by 3 will come out to be 1 milliamps, and this will be 3K, and this will be 4.7K, and this will be A and B, and this is 3.3K. Right, so now I can combine them again in parallel. So now the new circuit will become 1 milliamps in parallel with, this will be 3.3K A and B. So this will be 3K parallel 4.7K. Let me calculate its value. 3 into 4.7 divided by 7.7. So this is coming out to be around 1.83K. Right. So now we have come thus far. This is 1 milliamps. This was 1.83K, and this was 3.3K. Right, these is A and B. Now what I'll do, I'll again convert this to the Thevenin equivalent. From Norton equivalent, I'll again go back to the Thevenin equivalent. Yes, that's what we are doing. We are converting them back and forth as per our, if we see something in parallel, we go, for instance, we made them in parallel so as to simplify the current source, which are easier to simplify in Norton equivalent. When the resistances are to be added, we go to the Thevenin equivalent. So we are switching them back and forth as per our convenience. Now again, this can be switched back to the Thevenin equivalent now, right? So the voltage source will be 1.83. Remember, VTH equal to RTH times IN. So current is 1 milliamps and the resistance is 1.83, right? And this Thevenin equivalent will remain the same, and this will be 3.3K. So what we'll get is something like A and B, and now we can simply add up these resistances. So this will be 1.83 volts, and this will be A and B. So 3.3 plus 1.83 would be 5.13. 5.13K. This is 13K. So that solves the problem. So now we have arrived at this. This is what we are required. Remember, I told you, it doesn't care what's inside. We have to convert it to this form: one voltage source or current source and one resistance, and we have arrived there. So we have arrived there, and so we can see that the equivalent are Thevenin. So Thevenin voltage was asked. So Thevenin voltage, what we are getting is we are getting 1.83. So yeah, so option B, that's close enough. It's not exact, but it's close enough. Remember, we had simplified. We had assumed 3.30 to be equivalent to be 3K. So so we are close enough. So 1.86 volts is the Thevenin voltage, right? And next question, the same part of this question is, now they're asking about the Thevenin resistance. We have also calculated. Note, this was, so I'll change the I'll redraw this circuit over there. So what we have arrived here, we have seen that this circuit got converted to 5.13 volts. Sorry, not 5.13. This got converted to 1.83 volts and 5.13K. A and B. This is the Thevenin equivalent. So 5.13, the option is close enough, is 5.14. So we solved the same problem. We saw how to get the Thevenin voltage and the Thevenin resistance. And the key takeaway from this problem, I would say, is that that how did we convert from Norton to Thevenin and Thevenin to Norton based on the requirement. When the resistances are when required to be added, we went to Thevenin, right? And then when the resistances were in parallel, we got to Norton. And and that's the main takeaway from this. Yeah. So I'll pause here for a bit. If you have any doubts regarding this conversion from Norton to Thevenin, please ask. I'll pause a bit for a minute here. No? All right. Now we'll go ahead. So continuation to this problem is now we are going to ask, now it's asked from us the maximum power that can be delivered to a load. So what they are asking is that this is the circuit. Now I'll draw its equivalent circuit here first. So we saw that this was 1.83 volts and this was 5.13 k, right? This was A and B. So now the question that is asked of us is Norton method. You have to be specific which transistor circuits are you talking. See, for this here we are talking about linear devices only, right? All this methodology that we have been converting back and forth. All the resistors, these independent current and voltage sources, they are linear, right? Transistors need not be linear, and hence if you, so here the superposition theorem, all that is implicit in this. So transistors, I'm not saying it won't be. By linear we mean it's the more clarity is there in the lecture, but I'll just tell you what do we mean by linear. So for instance, V equal to IR, you see. So let's assume this is Y, R is a constant, it's M, and this is X. This is a straight line, right? So if let's say V1 equal to IR1 and V2 equal to I2 R1, there are two different sources, two different voltage sources applied across the same resistor. So simply we can write, if we can add them up. This is the principle of superposition actually. And there is no second order term, like there's no whole square or anything that is happening. This is what we mean by linear. These are linear devices. This is the linear analysis. Hence we are able to apply. Transistors are not necessarily, we can, for instance, there is some reason which they may be linear, but they are not always linear. So Norton, I cannot say it's by default it will be applicable. We have to make sure that the principle of superposition, and there are some other concerns. If they're satisfied, then yes, you can apply, but it's very specific. That's what I meant to say. Right. By the way, for linearity, Professor Mahesh Patil has explained in some depth what do we mean by linearity. So I request you to just revisit his lecture videos. Okay. So we had done that. Now we are required to find what is the maximum power delivered to a load. So let's assume there's a load that's connected here, right? So it's asking what is the maximum power that can be delivered to a load. Now if you go to the lectures, the maximum power is delivered. Can anyone tell me when is maximum power delivered to a load?
Load resistance is equal to Thevenin resistance.
Yes,
Thevenin's resistance.
so when RL equal to RTH. The proof of this, by the way, is in the video lecture. So RL equal to RTH. So this means this is equal to 5.13 K. And then you can simply say P equal to I square R. There is a formula. Can someone tell me the formula? The final formula that comes?
P is equal to V into I.
Oh, that is the formula for power. If you put RL equal to RTH, what is the power delivered to the load? Okay, I'll calculate it. I square into RL. I square would be VTH upon 2 RTH. That will be the current flowing times RTH, right? So this will be VTH square. So that's, sorry, I made a mistake somewhere. No, it's correct. VTH square over 4 RTH. Is it correct? Can someone confirm?
Yes, sir.
Yes.
Okay. So now I am just plugging the values. I'm not doing anything else. Let me plug these values in the calculator. So this will be 5.13. So it's coming out to be, I am getting 0.163. So I'm getting maximum power is 0.163 megawatts, because the current was in milliamps, the voltage was in volts, so that's why this value. So 0.163 megawatts, yeah, so 0.17 is close enough. Again, the options are far apart, so we need not be very precise, but we are close enough. This is the best option that we can get. So this problem, essentially the first three problems that we saw, they complete the whole picture, in which we saw to obtain voltage Thevenin equivalent, and then finally applying them to get the maximum power delivered to the load. So that completes the first part of our discussion regarding how to convert the voltages, the equivalents from Thevenin to Norton and vice versa, and finally power delivered to the load. Again, I'll pause a bit for here. So if there are any comments, please ask.
Sir, can you show the third question again?
Okay, here it is. You want the
Sir,
solution?
the simplification part that we
Okay.
had seen.
Here.
Sir, can you explain the second step again?
This one, power.
The calculation, sir, I square into
So
RL
okay, sorry,
to.
I made a mistake. So I is the current flowing through this circuit. So power delivered to the load, okay, will be I square times R. So I square times R. So I, what is the current? Current is this. Current will be VTH over RTH plus R. Can someone is unmute? Please mute yourself. Thank you. Someone is unmuted. Can you please mute yourself? Alright, I've taken care of that. So right, so I is VTH over RTH plus RL, right? And RTH equal to RL. So I will become VTH over 2 RTH, and that's the value I plugged there. Now it's clear? And now it's just the squaring and all. We're good?
Sir, okay, sir, but what about into RTH?
So RL value is RTH. That's what I've replaced the value of RTH. That's all I'm doing. RL equal to RTH. Please refer to this. RL equal to RTH. Since RL value is RTH, I've simply replaced that. So this is the power delivered to the load. Power delivered to the load. Power delivered to RL. Hence the formula is I square times RL. The value of RL happens to be RTH, which is 5.13 kilo ohms. That's, I'm only placing the value, just replacing the value. That's it.
Okay, so next step.
Next step, I'm just RTH, 1 RTH gets cancelled, VTH square over 2 square is 4, RTH square, 1 RTH gets cancelled, only this term remains.
Okay, sir.
Yeah.
Thank you.
Alright. So now let's move forward. So I remember for the first question I asked how to get the Thevenin equivalent. Someone told me the principle of superposition. So for the next 3 or 4 problems, we are going to talk about principle of superposition. And for more details, you can refer to the lecture. This is applicable when the circuits are linear, the devices are linear. Right. So let's go ahead. The question says, in the circuit shown in the figure, what is V2 when only VS1 is considered? So only we have to consider VS1. This means VS2 and IS are deactivated. What do we mean by deactivated? Deactivated means, I'll go here. So for this we only have to consider VS1. So we need to calculate what is the value of V2. V2 only considering VS1. Only VS1. This means this voltage source has to be deactivated, means this has to be shorted. Independent voltage source has to be shorted, and this one also has to be deactivated, means this has to be opened. No current can flow from here. So I'll draw this circuit over here again with these two sources removed. So this will be VS1, R1, R2 and R3. This is the only circuit now that remains. Alright. So now we are required to find V2, right? So I can simply say in order to, so this is the voltage that I need to find, this, and let's assume this is ground. We can just take it to be reference. It won't, I just simplify the algebra, and electrically it won't impact, right? So what I need is only I need to find the value of V2, right? So you can see that R2 and R3 are in parallel, right? So I can redraw this circuit as VS1, R1 will remain the same, and this will be R2 parallel R3, and this node is nothing but V2. You see this node will remain the same, and this is ground, right? So R2 parallel R3, R2 is 2, R3 is 2, so both are 2, so 2 parallel 2 will become 1. This is 10 volts, R1 is 4K, this will become 1K, and this is the value of V2. This is ground, this is ground. So simply this is a potential divider. We can write V2 equal to 10 times 1K over 4K plus 1K. So 4K plus 1K, 10 divided by 4K plus 1K will be the current flowing here, and if you multiply it by this resistor, you will get the value, right? I'll rewrite it in terms that it's clear to understand. V2 will be I times 1K. Ohm's law, V equal to IR across this resistor. The value of I will be simply 10 over 4K plus 1K in this loop times 1K. So this will be 10 by 5K into 1K. K and K gets cancelled. 10 by 5 is 2 volts. So we get V2 equal to 2 volts. So I have gotten, so is the correct answer? Yeah. So I have gotten V2 equal to 2 volts. Note, we have only considered VS1 and we deactivated VS2 and IS, right? There are some comments. Just hold on 1 second. Okay. Yeah. So that's the first part of the problem. There are other parts also which we'll go through now. So now what? So this is only VS1 we had considered now, right? So now the second part asked of this question, we only consider VS2, right? This is the circuit diagram. Now we have to only consider VS2, which would mean that again we are required to find V2 with only VS2. This means VS1 is an independent voltage source, so that will be shorted. IS is an independent current source, that will be open circuited. So I'll draw this circuit over here. So this will become R1. There's nothing over here, and then this is R2. This is R3. This is 8 volts, and this is the V2 that we are required to find. And again, I can, for all practical purposes, I can take the bottom node to be the reference node. Yes, Raja, go ahead. Raja, you may speak or write, because I'm not able to hear you. Just please write your doubt. Right. So now what we'll do, we are required to find this V2 value. So now I'll just redraw this circuit for just sake of clarity. So 8 volts will come here. This is R3. This is R2. And this is R1. This node is V2. I have just simply swapped the places. That's it. And I've done nothing else. So again, you can see R1 and R2 are in parallel, right? So what I'll do is that I'll again 8 volts. R3 value is 2K. And this will again be V2. This is ground. And this will be, this is 4K parallel 2K, right? So let me quickly get 4K parallel 2K. So that's 4 into 2 by 6. That will be 1.33K. Again, this is the potential divider. So again, I can write V2 is equal to, let's call this current I again, I times this value R. Let's call this R effective times R effective. So current I would be 8 volts divided by 2K plus 1.33K times 1.33K. This is going to be 2, so this is 3.33K times 1.33K. So 1.33K divided by 3.33K is 0.4. Yeah, so 8 into 0.4. So this will come out to be now 8 into 0.4 is 3.2 volts. This is question number 5. Yeah, so option D. and this is the correct answer. So we calculated that the value would be 3.2 volts. Again, we have only considered VS2. This means we shorted this and we opened this and we calculated the voltage across simply this resistor. Right. Just hold on a second. Why do we have to simplify R2 and R1? We can simply use potential divider rule, keeping R1, right? Okay, Nandita, if I can get your name correctly. The reason we have to do that, see, you're talking about why do we have to potential divider works when the same current is flowing, right? But you can solve it here itself without bringing. So if you want to solve this circuit, I'll solve this here, right? So that it's easier to understand. So this was 8 volts, this was R3, this was R2, and this was R1, right? So what you can simply assume current I1 here and current sorry, made a mistake. So this was R2, so you can assume total current I is flowing here and I2 is flowing here, and let's say I1 is flowing here. Let's make it I3. So first expression would become I3 equal to I2 plus I1 because KCL at this node, and then you can solve the values. Take this. There's one more variable V2. So there are enough equations and variables, and but you cannot directly apply potential. Potential divider is applicable when the same current is flowing. So here, for instance, the current flowing through R3 is not the same current flowing as R2. So you cannot directly apply the formula that we have for potential divider. For that to apply, the current has to be same through both the resistors, which is not it's I3 here and I2 here. So that's an important consideration. That's why I converted them, I made them in parallel. So now same current will flow through this R3 resistor and this R effective resistor, right? So that solves question 5. Now question 6 is a natural follow-up. Now it's saying we only considered IS. So I'll draw the same diagram. So again we are required to find V2 with only IS. What this would mean, if we need only IS, if we require to do only IS, then what would do? Deactivate VS1 and VS2. What do we mean by deactivate? Deactivate for an independent voltage source means shorting them. So I'm going to short both of these voltage sources. So what will I get? I'll get this circuit. R1, IS will remain as 1 milliamps like this. R2 will remain as it is, and so will remain R3. Okay, this is what I'm getting, and this is the V2 voltage that I'm required to find. If you look carefully, 1 milliamps is in parallel with did I miss something? No, we are good. So if you look carefully, that R2 and R3 are again in parallel. See, R2 has V2 and 0 across it, and R3 also has V2 and 0 across it. Come to think of it, R1 is also in parallel with all the three, right? So what I can do is I can simply draw this circuit. 1 milliamps R1, R2 and R3, and this node would be nothing but V2. I just put R1 on that side and did nothing else, right? So, and this is ground obviously. So now I can again draw this as 1 milliamps and R1 parallel R2 parallel R3, and this would be my V2. So let's calculate this R1 parallel R2 parallel R3. This would be 4K parallel 2K parallel 2K. So 2K parallel 2K is 1K. So that would be 4 times 1 by 5K. So that would be 0.8K. So R effective is 0.8K, and V2, if you simply apply the Ohm's law across this effective resistance, let's call it RF. This is R effective, REFF. So V2 will simply come out to be 1 milliamps times 0.8K. This will come out to be 0.8 volts. K and milliamps get cancelled. So what we are getting is it the correct answer? Option 6 is B. Yeah. So we are getting 0.8 volts, right? Not 0.8 millivolts, 0.8 volts. So again, only I is concerned. So this was shorted, and then we saw R1, R2, R3 coming in parallel, and we simply applied some algebra to solve the problem. There are a few raised hands. Okay, right. So now we have solved this problem. Just hold on a second. Yeah, we have solved this problem with this is the principle of superposition, by the way. So let me so this was the question given. So question from 4 to 6, we first took only VS1 and deactivated the other two, then we took VS2, deactivated the other two, then we took only AS and deactivated the other two, and that's how we did it step by step. This is essentially the principle of superposition. So using superposition, we determined the value of V2, right? So now it's asked in the circuit of question 4, what is V1, right? Here now this question says all three are activated, right? But we know that, so we have calculated V2, if you remember, right? So V2 was 0.8, then 3.2 and 2. So 2, 3.2 and 0.8. So I can simply say V2 we got was 2 volts plus 3.2 volts plus 0.8 volts. So V2 due to overall total V2 to combination of each of them would be 3.2 plus 0.8 is 4, 4 plus 2 is 6 volts. So V2 we got 6 volts, right? Just hold on a second. Yeah, so this value is 6 volts, and we are required to find the value of V1. That's all what we are required to find, right? So now this is very simple problem. Now we know, we'll again assume this to be grounded, and we know this node is now at 6 volts, and we need to find the value of V1. So V1 is nothing but this node minus this node. So let's label these nodes. This is VA, and let's say this is VB, and this is VC. So V1 I can write as VA minus VB, right? What's the value of VA? The value of VA is 10. What's the value of VB? VB is same as VC. No, there's a wire connecting them, so it's the same. And the value of VC is 6. So 10 minus 6 is 4 volts. So I got V1 equal to 4 volts. Note, all the three sources, voltage and current sources are active here. But since we have calculated V2, the cumulative V2 is 6 volts, we can simply plug in the value of V2, and then it's just very simple. Just reducing the two node voltages to get the value of V1. So we notice that V1 is 4 volts. So we got V1 equal to 4 volts. This is total due to all three. Again, this is due to total due to all the combination of all the three sources. So now we have calculated V1, and that is what we were required to find, right? So that again completes this problem. I'll again pause for a bit, and then if you have any doubts or comments, please feel free to ask. In this problem, in this set of 4 problems, what we had essentially done was use the principle of superposition to arrive at the corresponding voltage node voltages, and then we took them each of the sources one by one, calculated the required V2, the voltage across resistor 2, and then finally simply added them up in the last. So that's about this problem. If there are no more comments or doubts over this, let me go forward for the next set of problems rather. So this is the next problem that we have. It says that in the circuit shown in the figure, G equal to 0.5 mega. What's the symbol? Can someone tell me? This is symbol of what's that called? Conductance, right? Mho, it's called.
Simon or Mo?
Yeah, Siemens or Mho. It's if you reverse the order of ohm, you get Mho. So that's how I remembered actually. Right. So G is this. What is I2? Right. So we are required to find I2. I2 is this current, by the way. Okay. There's a hint. Use nodal analysis.
This is just a doubt in seventh problem.
Yeah.
Problem number 7. So why do we found the value of principal using superposition for V2 directly? We can find for V1 using superposition.
Yeah, we can, but that will take us another 20 minutes, right? Why to redouble the efforts when we already have V2 at hand, right? Why do you want to calculate V1? You can. It's not that you can't. the first three problems, problems 4 to 6, made us calculate V2 using principle of superposition. Now we know V2, right? Now we know V2, and it's a very simple expression to very simple way to get to V1. That's why we are not using. You can to answer the question, you can, but it's not worth the effort when you can already get V1. It's pre-cooked. Why you want to get all the ingredients and cook it all the way again? For practice it's good, but for solving here, the idea, the point of question number 7 was to show you the importance of superposition. Once you get any voltage or current through superposition, you can get other voltages and currents in the circuit without using superposition, because you already know the voltage or current. In this case it's voltage. For instance, they could have asked us to calculate the current through R3. If you knew R3, total R3, then we could calculate VC, VA, VB, everything with ease.
Okay, sir.
Yeah, right. So yeah, we were talking about this. So it says that hint is use your nodal analysis. So nodal analysis, we label the nodes and we get the voltage and everything. Take C as the reference node. So we ground C is this. So we ground this. So let me ground this. Reference is, this is at 0 volts. This means assign node voltage is V1 and V2. Okay, so everything is given, right? KCL nodes and solve for V1 and V2. Yeah. So this is how very crude method, so to say. Okay. So what's we are required to find I2. So we are required to find I2. This is grounded. This is V1. Okay, and this point is V2. Now it says we have to write. So first let's identify the unknowns that we have in the problem. Okay, we don't know I2. We don't know I3 either. We don't know V1. Yeah, we don't know V1. And we don't know V2. So these two nodes, the current over here, and yeah, here we know the current, but we don't know the current here also. Fine. So what the question says, write KCL equations at node A and B. So first let me write KCL at node A. So KCL means incoming current should be equal to outgoing current. So node A. So this is the incoming current, right, from the left. So I'll let incoming current is IS, right? And what's going to happen is that so there'll be current flowing out. So there is a current flowing. It's given I2 over here, and let's assume that I1 is flowing in this direction. So this will be I1 plus I2, right? I1 plus I2. Similarly, if I write KCL, so there is one more variable, I1, I2, V1, V2, then KCL at node B. So KCL at node B would be incoming current is I2 plus GV1 and outflowing current is I3. Okay, so there are too many variables and I'll get confused. So the way to solve this is to convert everything to voltages. That way, because there are only two voltages, there are three currents, but there are only two voltages. So we'll at least get rid of one variable, right? So IS will remain the same. IS will remain 4. The value of I1, if I apply Ohm's law across R1. So Ohm's law across R1, I can write the voltage across R1 is V1 times I1 times R1. The I1 will, so I1 times 1k, this is V1. So I'll get I1 equal to V1 over 1k. Let's put this value over here. By the way, this is milli. So I1 is V1 over 1k. Good. What is I2? I2 again, Ohm's law. Excuse me. Okay, this is the present. So Ohm's law across R2, I can write V2 minus V1 is the potential drop across R2. This is equal to, sorry, it will be V1 minus V2, high minus low, equal to I2 times R2. So I2 will be V1 minus V2 over 2k. The value of R2 is 2k. I'll again put this over here, V1 minus V2 over 2k. I'll take k to the other side. K and m will get, this is milli, this is kilo, they'll get cancelled. So I'll get 4 equal to V1 plus V1 minus V2 by 2. So I'll get 8 equal to 3V1 minus V2. I just took the LCM. This is my first expression. Okay, again I'll do the same for this. The value of I2 is V1 minus V2 over 2k plus the value of G, I think, was 0.5 milli if I'm not wrong. Yeah, 0.5 milli. V1 will remain the same. For I3, again I apply Ohm's law here, so that will be V2 minus 0 over 0.5k. 500 ohms is 0.5k. Right, so again I'll take no, first let's write this. Let's eliminate k. So this will become, so k into milli will become 1. So k, you can take k as LCM, so this will vanish, equal to V2 by 0.5. This will be V1 minus V2 by 2 plus V1 by 2. This will be 2V2. 0.5 is in denominator. So this will become, now take the LCM as 2. This will become V1 minus V2 plus V1 equal to 4V2. Right? So now I can get 2V1 equal to 5V2. 2V1 equal to 5V2. So this is the first expression. This is the second expression. So what I'll do now, I just need to solve them. Right, so how to solve them? Let's calculate the value of V2 from here. So V2 will be 2 by 5 V1 and put it over here. This will give me, I'm solving them here on the next slide. So 8 equal to 3 V1 minus V2 and 2 V1 equal to 5 V2. So I get V2 equal to 2 by 5 V1. Let's put this here. So this will be give me 8 equal to 3 V1 minus 2 by 5 V1. This will be 40 equal to 15 minus 2 is 13. So V1 will come out to be 40 by 13 volts. So I have got V1, but I was required to find I2. Right, if I need I2, I need V2 also. Okay, so this implies V2 I can get 2 by 5 times V1, 40 by 13. So this will come out to be 16 by 13 volts. So this is V2, and I know from this expression that I2 equal to V1 minus V2 over 2k. So let's put the values. 40 by 13 volts minus 16 by 13 volts over 2k. So 40 minus 16 is, I think, 24 volts upon 26k. So 24 by 26 would be 0.92. There's k in the denominator. Sorry, this was kilo ohm actually. So volts over ohm is amps. So this will be milliamps. So what I'm getting is, for question number 8, I should get D. So we are getting 0.92 milliamps, which is the option over here. By the way, I forgot to mention, this is a voltage, a current source. This is a current source. How do I know it's a current source? There is an arrow inside it, but it's not encircled in a, it's not closed in a circle, it's closed in a diamond. This means it's a dependent current source. Similarly, this is the symbol of a dependent voltage source. You can see that this current source is dependent on some voltage V1. This is not independent. This is independent. Whatever is happening in the circuit, this source doesn't bother. It's always give 4 milliamps. This one bothers. This one depends what's the value of V1. If the value of V1 is 0, there will be no current. If the value of V1 is 1, the value would be 0.5 milliamps, because G is 0.5 millimole or millisiemens. Right, so that was the problem. I guess we have solved the problem. I'll pause here for a bit. If you have any doubts or comments, please ask. This was just a simple nodal analysis. This is, I guess, maybe in secondary, higher secondary, I think the T set. I'm forgetting. I'm getting older. Right, so now let's move forward. Now it says, what is the value of I3? Okay, so remember, this was V2, right? And this was ground. So I3 would simply be V2 minus 0 over 500 ohms. And we calculated the value of V2 somewhere, I remember. V2 was 16 by 13 volts. So I'll write 16 by 13 volts divided by 0.5k, because answer usually milliamps, kilo ohms. This will be milliamps, so this will be 32 by 13 milliamps. Please note that I had already calculated V2 for the last question. I am just placing this value here, I'll use my calculator. 32 by 13 is around 2.46 milliamps. This is question number 9. Answer should be A. Yeah, so there is 2.46 milliamps. This is what we have obtained over here. 16 by 13 over 0.5 kilo ohms. So that's the complete problem. Okay, so that's the second part for this problem. Any doubts, or I can move forward? This is very simple analysis. Once you find voltages or current, it's just plug and play. You just plug this value over there, from calculate from here, plug over there, and that's it. It's very straightforward. There's nothing much to do actually. Right, so question 9 we have just discussed. I3 value is 2.46. So this completes the third set of questions. So just to summarize, I'll go to the question. Yeah, in this this was the circuit given to us, and this was a unique circuit. Let me go to question problem 8 itself. Yeah, over here this was the problem given to us, and this was a dependent current source, and to be more precise, voltage controlled. This is called voltage dependent current source. This is a current source, but it depends on the voltage. Hence these kinds of sources are also known as voltage dependent current source or voltage controlled current source. We were given that, and the question itself gave, to be honest, too many hints. We used the nodal analysis, so we put the values v1 and v2 over here. We wrote KCL for node A and node B, and we got two variables v1 and v2 and two expressions, and we just solve those two equations, and we got the value of v1 and v2. And once you get v1 and v2, you can simply, using the Ohm's law, get I2, I3, I1. You can get every current and voltage in this circuit for that matter. So that was the problem 8 and 9. Now we'll go ahead and start discussing problem number 10. Okay, so let's go ahead. You have any comments or questions, or can I go ahead? Just please respond. If I'm going too fast, or if you want me to repeat something, please ask, because we have plenty of time. We still have around 50 minutes left, and we are more than halfway through the questions. All right, if not, then I'll move ahead. So again, this is a very interesting question. The question says, in the circuit shown in the figure, VA is given by this expression K1 V1 plus K2 V2 plus K3 V3 plus K4 V4. This is the expression. Yeah, go ahead. Praveen, yes, this session is being recorded, and I'll upload the recording hopefully by tonight itself, after some requisite editing. And you can visit this YouTube channel if you are interested in revisiting the video. Someone was saying something. Can you please repeat yourself? Okay, Nandini, what are the basic topics we must know for better understanding these classes? Are you talking about the classes that I am conducting, or the classes that Professor Mahesh is, the lectures that are there? For these classes, for the sessions that I am taking, you simply need to go through the lectures, recorded lectures that are there on the Swayam portal. This is directly from that. Whatever I am discussing here, it's nothing that I am making up. In fact, these are the problems which are the previous year problems from this course itself. These are very relevant. These are very relevant to the lectures that you can see on the Swayam portal, and if you need further in-depth understanding, then I guess there must be some reading materials which the TAs can provide, if you still insist. But as of now, what we are talking is higher secondary physics, if I'm not mistaken, or maybe bachelor's level, first year, second year. This is very simple. Superposition principle, V equal to IR. If you still find some confusions or some you need better understanding, I request you to just watch those videos again, which Professor Mahesh has which is recorded videos which are there. And if you still feel some doubts, there's a discussion forum. You can post your comments or doubts over there, which people have done. And if anything related to these problems that I'm discussing, you are feel free to email me. All right, so I guess that okay, yeah, so I guess I've answered her doubt. Right, now we move ahead. So VA is given, it's in the problem it says that VA is given by this long expression dependent. So V1, V2, V3, V4 are 4 node voltages, and VA sitting at the center is dependent like this. We are required to find the value of K1 and K2. So this is actually what I mean by superposition. So VA is dependent on V1, V2, V3 and V4, and this K1, K2, K3 and K4 that you see, these are some constants. These constants will depend obviously on the value of the resistors here, the 4 resistors that we have, but these are constants. Okay, so what the question asks now there are multiple ways of doing this. The most relatable way that I'll talk about the way which I approach this problem. So it's given VA equal to K1 V1 plus K2 V2 plus K3 V3 plus K4 V4. Okay, sorry, yeah. So we are required to find the value of K1 and K2. So first let's just find the value of K1. If you look carefully, what I can do, if we put V2 equal to V3 equal to V4 equal to 0 volts, this is actually superposition. I am deactivating V2, V3 and V4. These are independent voltage sources. So if you put these 3 equal to 0, that's what we mean by deactivating. I get VA equal to K1 times V1, right? This is what I'll get. So let's do that. Let's make this grounded. 0 means grounded, this to be ground and this to be ground. So how will the circuit look then? I'll draw this over here. So this is V1, this is VA, this is V1, right? And then from over here, this is R2, this is grounded, 2K, this is R4, this is also grounded, it's connected to here. Also this is 1K, this is R3, this is also grounded, right? And so this is the voltage source that we have. So I can replace this by something like this. Now you can clearly see what I mean. Now this is a familiar form that we have. This is V1, right? So now what's happening is that, so whatever, and this is by the way R1, whose value is 1K. So now this again R2, R3 and R4 are in parallel. So I can redraw this circuit as V1, R1 which is 1K, this is VA, this would be R2 parallel R3 parallel R4. This is the same thing that we had done, I think, in the first problem or second problem that we had. Yeah, Raja, go ahead. And if and then you may write also. I don't think I'm able to hear you. Please write. Okay, right. So R2 parallel R3 parallel R4, and this is the value of VA, and then this was grounded. So R2 parallel R3 parallel R4, so that means 2K parallel 1K parallel 1K, 1K parallel 1K will be 0.5K. So and this will come out to be 2 into 0.5K over 2.5K. So this is 1K over 2.5, sorry, 1K over 2.5. So 1 over 2.5 I think is 0.4. Yeah, so this is coming out to be 0.4 kilo ohms. This effective resistance is 0.4 kilo ohms. Now this is just a simple potential divider. So I can simply say VA equal to, again let's assume current I is flowing. So VA will be equal to, and let's call this R effective. This will be I times R effective. The value of I would be V1 divided by R1 plus R effective times R effective. I'll write this over here. I ran out of space. So V1 will remain the same, and R effective is 0.4K divided by 1K plus 0.4K. 1K plus 0.4K. So this will come out to be 0.4 by 0.1. So this will come out to V1 into 2 by 7. So we have obtained that the coefficient K1, this implies K1 is 2 by 7. Is it one of the options? Yes, it is one of the options. So option B must be the correct one. Yeah, but that's half the picture. Remember, we also need to find K2. So I'll again write the expression K2 V2 plus K3 V3 plus K4 V4. Again, if I deactivate V1, V3 and V4, right? So VA equal to K2 V2 if V1 equal to V3 equal to V4 equal to 0. Ground this, ground this and ground this, and I'll draw the circuit over here again. So this is V2. Again I'll draw this like the same form, V2 over here. This is 1K R2, right? And this is the node A that we have over here, right? From node A there are three resistance emerging. This is R1, this is R4 and this is R3, right? And this is ground. Again I can draw the equivalent circuit. This will be V2 1K, this will be VA, and this should be R effective equal to R1, the value of 1K parallel 2K parallel 1K. I'm doing it correct, right? K2 V2, yeah, 1K and 2K. Okay. So this will again come out to be 2K parallel 0.5K. This will be 2 times 0.5K over 2.5. So this will again be 0.4K. So this will exactly be the same like the last time. So again I assume current I. So VA will be equal to I times R effective, which will be equal to V2 over 1K plus 0.4K times 0.4K. This will come out to V2 into 0.4 divided by 1.4. So again VA is again coming out to be 2 by 7 times V2, just like the previous one. For some reason it's 1 by 7, which I don't think is correct, because V1 and V2 are effectively the same. They're interchangeably used. So B is the correct option. This is wrong. This has to be 2 by 7. Alright, so this is again a very simple problem which only included the use of principle of superposition, and that's what we have done here. Right, so yeah, so that solves this problem. In case there are any comments and question, I'll pause. Do I have some hands raised? Just hold on a second. Anonymous, please speak up. That's a nice name. Alright, I'm not able to hear anything. So can you discuss question 4 from assignment 1? No, I cannot. Because that's for your evaluation. If you have any doubts, some specific doubt in that question, post it in the discussion forum, email me or other fellows which will take the sessions. But we cannot discuss the question itself directly. You have to solve it. If you find some specific problem, email to us, we'll respond. So that's not a problem. We cannot solve the question in the class. In the next week, however, if you still have some problems after the solutions are uploaded for assignment 1, then we can surely discuss, because now the solutions are in the open. But right now, unfortunately, we cannot. If you have some specific conceptual doubt, please ask. That's a different thing. But we cannot talk about the solutions directly. Alright. Now moving forward for question number 11. So question says current I in the circuit shown in the figure is plotted versus voltage V, which gives a straight line. Okay, so we are plotting I versus V. This means this is the y-axis, this is the x-axis. It says it's a straight line, so this means I'm getting y equal to mx plus c. What is the intercept of the straight line on the v-axis? So v-axis means on the x-axis. So on x-axis y is equal to 0. So if you put y equal to 0, you will get some voltage value. So we are required to find that value, whatever that is. So we'll go ahead and do that. So essentially we need to find this expression I versus V, whatever that may be. Excuse me. right? So yeah, so we'll go ahead and try to evaluate I versus v to get y versus x. Okay, so this is the problem that we have. So there's a v and there's an I. So what I'll do is that I'll redraw this circuit. I'll redraw this circuit in the following manner. This is 1 milliamps. This is R1. This is R2. This is how I'm drawing this circuit. Okay, and let's assume this is ground. I've taken it to be the reference voltage. Okay, now moving ahead. So now this is 1 milliamps again, so current here also would be 1 milliamps, right? And current here also would be 1 milliamps. Let's label this node. Let's call this node V1. Okay, so what I'm going to do, I'll try to evaluate the value of this node V1, and let's call this current, the current through this resistor, as I2. Okay, so how to get V1? It's very simple. You can see that the current here is flowing is 1 milliamps. Sorry, the value of V1 would be exactly V. I beg your pardon, because this is a wire over here. Excuse me. Yeah, so V1 would be exactly be equal to V, right? Now what I can do, yeah, I'll apply KCL at node 1. I'm calling this node 1. So what's going to happen, the incoming current, which is I1, sorry, which is I, should be equal to 1 milliamps, which is going out, plus this current I2, right? So I get I2 equal to I minus 1 milliamps. This is the first expression. Now I'll simply apply Ohm's law across R2. Let's do that. Ohm's law across this resistor. So that would be V. So the voltage is V minus 0. V minus 0 equal to I times R, the current flowing through I2 times R2. So I2 from this I'll get is V by R2. This is expression 2. Both are the same value of I2, so I can simply equate. I can write I minus 1 milliamps equal to V by R2. The value of R2 is 1 kilo ohms. Okay, now we are required to, I'll write this expression over here again, I minus 1 milliamps equal to V over 1k. So this will come out to, so let's assume the units of I are in milliamps. Okay, so I'm dropping the milli over here. There's also k here, so this is also in millivolts. So I can simply say I minus 1 equal to V. Note, this was Y minus 1 equal to X, or if you insist, Y equal to X plus 1. This is what we are getting. Okay, Y equal to X plus 1. So it's asked, so we can also plot, we can also draw this, sorry. So this is Y and this is X. At X equal to 0, Y is equal to 1, so somewhere over here. And at Y equal to 0, X equal to minus 1, so somewhere over here. This is minus 1, this is 1. This is how this will look like. And we are required to find the intercept of straight line on V axis. So intercept of straight line on V axis, this is the V axis, the voltage axis, this is the current axis. This is coming out to be minus 1. So we find the X intercept equal to minus 1 volts. So this is problem number 11. We get minus 1 volts. Answer should be D according to my answer. Yeah, so D is correct. That's what we did. This is nothing but simply just writing the, this is you cannot get a more simpler problem than this. Just writing the node voltages and Ohm's law, and we got the answer. That's it. Straightforward problem. So that's it. Now we'll move forward. Says now a follow-up to this problem is the plot of question 11. What is the intercept of I versus V line on the x-axis? So we drew that, right? We drew that something like this. This was -1, this was 1. This is I in milliamps, this is voltage in volts. So this should be, this was 1, remember? So the value of 12, just hold on a second. Just give me a minute. I should be equal to I2 plus 1, that's correct. I should be equal to I2 plus 1, I2 should be I minus 1, V should be I2 times R2. So I minus 1 should be equal to V by K. Yeah, so that is correct. Fine. So we are getting as 1 milliamps. So I guess the polarity has been reversed. I guess that's the only thing that's of concern here, but the magnitude is 1 milliamps. You can see the magnitude. So the closest option that we have is option B over here. I may have made some sign mistake, or I don't know. So but the concept is straightforward. So this is what we are getting. All right. So now, okay, right, excuse me. Okay, so now it asks is that if the resistance is connected between A and B in the circuit of Q11, what value of R will maximize the power absorbed by the R? So now what it's asking is that essentially the Thevenin equivalent. So if I connect a resistance R here, so what will be the value at which this will be maximized? So essentially it's we are being asked to evaluate the Thevenin equivalent. By the way I did the analysis that I did, the I versus V, you can also do it through the Thevenin, using the Thevenin equivalent also, right? So what I'll try to see, how to maximize power when R load equal to R Thevenin. So what we need to do is simply need to find the Thevenin equivalent of this circuit. So that's fairly simple. How to find the Thevenin equivalent? You deactivate all the independent current and voltage sources. So there is only one current, there's only one independent source. So we'll deactivate means we'll simply open this. So what will remain is R2, R1, and this has been opened, and this will be your, so whatever voltage you will get over here, that will be your RTH between A and B. That will be your RTH. So what you will get is no current will flow through over here. So what you will get, RTH will be nothing but equal to R2. So that would be 1 kilo ohms. Yeah, this is the answer. This is the 1 kilo ohms is what we are getting. I'll just repeat myself what I did over here. Since this is open circuit, no current can flow through here, so this resistor gets dropped. So this will get converted to like this, A and B, and this is R2. So RTH will be nothing but R2, and the value of R2 is 1 kilo ohms. We plug in over here and we get the option C. So this is the third part. Yeah, now in the so in the question, in the circuit of question 13, the previous question that we had discussed, the maximum power that can be delivered to a resistance between load A and B. So again we had done that. So we saw that P max was, I forget what it was, expression. Can someone remind? This was I square RTH. We saw I square is VTH over 2 RTH whole squared times RTH. This will be VTH whole square over 4 RTH. Now we know RTH, we just need to get the VTH that we need. So VTH, we can simply so whatever this voltage V that we had gotten was essentially nothing but VTH. Remember that this is the essential, this is how you find VTH, plus minus, and you just whatever the voltage that you get across it, forget about I for the time being, and this is how we find VTH. So that's what we had done earlier also. So VTH, if I remember, was 1. So this will be 1 volts by 4 into 1K. So So that will come out to be 0.25 milliwatts. So 1 square actually. That's coming out to be 0.25 milliwatts. So answer should be B. Yeah, answer is B. Yeah. So again, this question was disguised. I could have solved this using the Thevenin approach, right? Using VTH and RTH. Remember, you find out I and V. I deliberately did not. The reason was just to show you that nodal analysis and someone is, can you mute yourself? Okay, thank you. So Thevenin or Norton analysis, they give the equivalent. So we solved, for instance, for problem 11 to 12 we used nodal analysis, and 13 to 14 we used Thevenin, right? And you see the values that I obtained in 11 12 I directly using 13 and 14, and we still got the correct answer. The way I did it this way is just to emphasize that whatever approach you feel comfortable with, you can use that. Sometimes a nodal is better, and sometimes Thevenin is better, and it also depends on your comfort zone. So which approach you are more comfortable with, I suggest you choose that approach, right? So I'll pause for a bit over here, and if you have any comments till now, whatever we have discussed, I'll just summarize in a few seconds. So till now we had talked about two major things. First we talked about was the Thevenin and Norton analysis. So in the first 4 problems we had talked about how we interchangeably convert from Thevenin to Norton, Norton to Thevenin, in order to arrive at the final Thevenin equivalent. And we saw that if we wanted resistances in parallel, what we did was we went to Norton equivalent. If we wanted resistances in series and we wanted to add them up, then we went to the Thevenin equivalent, and we kept on interchanging them until we arrived at the final Thevenin model, or Thevenin equivalent. So that's what we did, and then after that we solved a couple of problems on specifically focused on the principle of superposition. We saw that which we had two voltage sources, two independent voltage sources, one independent current source. In that, what we had done was that we solved them using beg your pardon, I'm forgetting. Yeah, we deactivated the two sources, and then we solved from one. And the second problem, we deactivated the second one. We activated the second one, deactivated the other two, and then we went ahead and added up the voltage values to arrive the final value. And finally, we saw that cross kind of structure, R1, R V1, K1, V1, K2, V2, K3, V3, K3. That was also superposition. And finally, in this problem, what I emphasized was that whether you do nodal analysis or you do Thevenin equivalent, they are both the same. So whichever one you want, you can choose that. Now we are going to talk about phasors. So that's why I again request you, if you have any comments or doubts, please feel free to ask. If you have any other questions that you want me to discuss in the class, please go ahead and ask. I cannot solve the problems of the current assignment, but if you have any other doubt, please ask, because we have sufficient time at our hand. We still have 30 minutes, 27 minutes, and only 2 questions are left. So feel free. I'll pause for a bit and wait for the responses. All right. If not, then we'll go ahead and we jump into something called phasors. So as in the videos, in the lecture videos, the phasors was talked about. So I'll again briefly visit it, because it might be new for some people, especially for the first year learners. So what essentially a phasor is that, so for instance, I'll use the same example that was used in the lecture video. So what's happening is that, excuse me, okay, sorry. Yeah, so this is a resistor and a capacitor. So initially capacitor is uncharged, initially, right? This means Q t equal to 0 is 0, or you can say voltage at t equal to 0 equal to 0. The way this follows is because Q equal to CV. Q is the charge stored on the capacitor, C is the capacitance, V is the voltage applied across the capacitor. So, and let's say you are applying some voltage, and this is the DC voltage, and you also apply an AC voltage, right? So if I forget about AC voltage for the time being, and we know that the charging time, it will be something like V, and let's say this is Vm, V max, this will be Vm e to the power minus t over RC. If you write the KVL in this loop and you solve this differential equation, then you get something like this, where this is V out, so this is, or VC you can say. The voltage on the capacitor will be Vm e to the power minus t over RC. There should be one minus also, sorry, it will be like this, because t equal to 0, the voltage has to be 0, right? So this is what we get, and you see that at when t tends to infinity, what will I get? Vc equal to Vm 1 minus e to the power minus t by RC. When t goes to infinity, this term will go vanishingly low, this will become 0, so this will become Vm. So we can say that at infinite time, the capacitor will get fully charged. By fully charged, we mean the voltage stored by the capacitor now will be exactly equal to the source voltage, the voltage supply that we are charging this circuit with, that is Vm in this case. Now what I'll do is that I'll assume that Vm, this voltage source, is not purely a DC voltage source. This also has an AC component. So what I'll do is that the way we denote AC is using this symbol. This denotes an AC voltage source. Okay, so what I'll do is that now this V, this is not simply Vm, this is Vm, let's say cos omega t. So if I draw its waveform, it will look something like this. This is time axis, this is your V input, this is V input. So V input would be, at time t equal to 0, it will be Vm, and it will oscillate like this. This is minus Vm. It will keep on oscillating. Now what's going to happen? Now intuitively, it's safe to assume that you will again assume that at time when t tends to infinity, the capacitor would have fully charged, right? This means the capacitor would fully reflect whatever the input voltage supply there was, and that's what we would come to expect. So what's going to happen at t equal to infinity? This means if the input voltage now it's oscillating, is itself oscillating. Now the output, the voltage that will appear across the capacitor will also have a sinusoidal component, right? It won't have a DC component, but because that will stabilize at whatever the value is, but it also the DC value, that is, but it also is sinusoidal component, or the AC component, which we may call. And this is referred to as, by the way, sinusoidal steady state. This means that it's oscillating nicely over some reference like this. The output would, just like the input voltage. This is what we mean, it's reached a set. It's sinusoidal, yes. It's not constant. It's not. It's varying with respect to time. True, sinusoidally varying with respect to time, but it has achieved a steady state. Means it's not. Means its average value remains constant. So, for instance, this V in signal has average value of 0 volts, right? So this output voltage that we are seeing over here will also achieve that steady state, and the way to represent the steady state, we do it by using something called phasors. We use something called phasors to represent sinusoidal steady state. The other reason we do it is that because it often becomes cumbersome to operate signals which are time varying, because then if there is cause, like for instance there might be some terms involving integration and differentiation, and that usually causes a lot of trouble. So in order to avoid that, we have arrived at some scheme called the phasors, right? So what are the phasors? Is there a comment, a question? No, okay, sorry. So what I was saying, yeah, I was talking about phasors, right? So what we'll try to do is that we only try to represent sinusoidally steady state in terms of phasors. So what I mean was that, so there will be some component, we denote by, let's say, x, right, xm. This is how your signal will look like. So your x can be, for instance, your x can be your voltage or your current, right? So it will have this form, this equal to some constant times cos omega t plus phi. This component has to be there because it's sinusoidally varying. Now what we do now is that we try to omit this term, because we assume that it's always there, right? So what we do it is that we write it in this way. This is how usually complex numbers are represented, right? There's a magnitude at the front, right, and there is a phase associated with that. So for instance, if I try to represent z equal to 1 plus iota, right, so how will I do that? So first I'll calculate mod z. So mod z would be 1 squared plus mod iota squared, so that will be, sorry, not mod iota, it's iota times 1, so 1 square plus 1 square, so that will be root 2, right, and theta would be tan inverse y by x, right? So y is 1, x is 1, so tan inverse 1, that's 45 degrees. So I can represent this z, this 1 plus iota, as root 2 angle 45. That's how the representation works. Now this is in degrees. Sometimes it's preferable to use radians. So we know that pi is equivalent to 180 degrees. So 45 degrees will come out to be pi by 4. So then we can write it as root 2 angle pi by 4. So this is the representation for that. This is the complex number representation, by the way, and that's the similar thing we follow over here. So for instance, and please remember that we are omitting omega t term, the sinusoidally varying term we are omitting. We are only interested in using the representation. We are only concerned about that what is the phase. That's the only thing we want to talk about. So this is a brief overview of the phases. I request you to go through the lecture. It's very beautifully explained there why we need phases and what's their utility, right? So now the question asks is, what is the phasor corresponding to 5 cos omega t minus 53 degrees? So I'll solve it over here itself. So 5 cos omega t minus 53 degrees. Okay, so now as I told you, so we omit omega t term, so we will forget about this term, right, and compare with this format. So again I told you this x can be voltage or current, so this is given in this format. So I can simply write this is equal to 5, the maximum value is 5, so or the modulo is 5, so that remains same, and this comes out to be minus 53 degrees, because remember it's plus theta, so here theta value is minus 53, and that comes as it is. Alright, so now we have obtained v. So I write it as x equal to 5, and the phase is minus 53 degrees. Now the questions asks us to convert it into the x plus iota y format. So we know how to do this, right? So this will be 5, the magnitude will stay out, this will be cos minus 53 degrees plus iota sine minus 53 degrees. 5 will remain the same. Cos minus theta is cos theta, so that will be cos 53. The minus will come out, so minus iota sine 53 degrees. Cos 53 is it 3 by 5 or 4 by 5? It will be 3 by 5, I think. Yeah, sine has to be bigger, correct. Minus iota 4 by 5. Just excuse me. Okay. So where was so we were over here. So you multiply the 5 inside, you will get 3 minus 4 iota, and note that this was voltage, so the units would be somewhat in volts. I'm getting option should be A. Yeah, 3 minus 4 iota I was getting. So option A is the correct one here, right? So again, I'll in the next problem also I'll reiterate the concept of phasor. Here it's just a theoretical part. It's essentially whatever the sinusoidal steady state is for the signal, we represent it using a phasor, and since it's steady state, we usually omit the omega t term, and whatever is left we represent in the using the complex analysis or the complex nomenclature using x plus iota y, which is done using here, or in the polar coordinates in this form, like I told you the example of the complex number z, which is 1 plus iota. So there are different ways to represent. This is the x plus iota y format, this is the polar format, this is the coordinate format, this is the polar format. Same thing we did for this problem. So this was a very straightforward problem in the last one. Here it's a bit more involved. So here there are few other things that you need to know. So for instance, in resistance is denoted by R, you know that. Inductance is denoted by L. Capacitance is denoted by C. When working in frequency domain, right, so we denoted them by the underlying electrical characteristics remain the same, but the way we denote them becomes different. So here we denote it as ZR, you can say ZR. So that will be equal to R plus J0. So this is the real part, this is the image. So there is no imaginary part associated with the resistor. So I'll write it over here. ZR equal to whatever the value R is plus J into 0. You can say this is purely real. By the way, Z is the symbol for impedance, right? So impedance has real part and imaginary part. We'll just see it in a minute. ZL, impedance associated with inductance, that would be 0 plus J omega L. This is purely imaginary. Right. Similarly, ZC, impedance associated with capacitance, this is again purely imaginary. And this Z, just like we have, like if we have two resistors in parallel, right, R1 and R2, we can simply say R effective equal to R1 parallel R2. A similar concept exists here also. This is Z1, this is Z2. So Z effective would become Z1 parallel Z2, where Z1, if it's a resistive component, it's given by this. Let's say if Z2 is inductance, which is the example here, it will be given by 0 plus J omega L. Why do we do this? If we convert it to this format, the impedance format, we can simply apply all the rules that we have for instance, in parallel, R effective becomes R1 plus R2. All the analysis, the Thevenin, Norton analysis, and the Nodal analysis that we had discussed for resistors becomes, and there the signals were not time varying. The signals were the DC signals, they were constant over time. They may be pulsing, but they were not sinusoidally varying. There's no frequency associated with them. In this case, if we come in the frequency domain, and if we introduce L and C, then you will encounter differential equations which analytically they are difficult to solve, right? So a better way to solve it on paper or from software is to convert everything to frequency domain. And if we use this impedance scheme that we have over here, then it becomes very straightforward to solve the problems, because essentially now we will be treating everything just like we did in the DC domain. So AC domain gets analytically gets a counterpart in the DC nodal analysis and the Thevenin, and accordingly also the Thevenin and the Norton analysis that we had talked about. Right, just hold on a second. Are you able to see my screen? Because I am not. Can someone respond? What do you see on your screen?
Yes, sir.
Yes, sir.
Question 16 is visible?
Yes, sir.
Okay, fine.
Yes, sir.
Because for some reason I don't know what happened. Okay, so I'll try to solve this problem now. So I'll draw this circuit over here. So this is 8 ohms. We are required to find this. So let's just make it R and L, and we are required to find Z, and we have been given frequency equal to 50 Hertz, which comes in our ohms, and so L is 20 millihenry, the unit is Henry, and R is 8 ohms. We are required to find the value of Z. So you can clearly see that these are in parallel, right? So I'll redraw this circuit now as this. I'll call this ZR, and I'll call this impedance as ZL, where ZR would be, I told you, it will be the value of resistance, which is 8 plus J into 0. There's no imaginary component. On the other hand, ZL would be 0 plus J omega L. So J omega is nothing but 2 pi f, where f is the frequency of oscillation. So it will be omega. We can calculate the value of omega and put it later. And L is again 20 millihenry. So these are numerical values which we'll put later, no need to bother. And this is the Z effective. Z we need to calculate. So I can simply say Z equal to ZR into ZL over ZR plus ZL. So value of ZR now we have to put is 8. This times J omega L, right, divided by 8 plus J omega L. What is the format of options? Okay, so now we have to remove the imaginary term from below here. So numerator will become 8 omega L, and we multiply it by its conjugate, so it will be 8 minus J omega L divided by, so this will become 8 plus J omega L times 8 minus J omega L. So the numerator will come out to be, excuse me, yeah, so numerator will come out to be J into 8 omega L times 8 minus J omega L, that remains same. This will come out to be 64 plus omega square L squared, right? Now I have no option but to put the values, so this will come out to be 100 times pi. This will be radians per second. So 100 times pi, so this will come out to be J into 100 pi into 20 millihenry. So these zeros get cancelled with milli, so I'll get 2 pi, J into 2 pi, everything gets cancelled, right? So J into 2 pi, so I'll put this value over here. Yeah, so this comes out to be effectively omega L is coming out to be 2 pi. That's the takeaway from here. Okay, so this will come out to be J times 8 times 2 pi, 8 minus J into 2 pi divided by 64 plus 2 pi whole squared, right? So now what I can do is simply multiply the J term inside. So what I'll get is the first term will become 16 pi into 2 pi, 16 pi into 2 pi, this is 16 pi into 2 pi plus 16 into 8 is 128 pi, this will be J, right? And this will be 64 plus 2 pi whole square. I'll just get my calculator because this is now getting a bit too much of calculation, that is. So pi into 2 whole squared plus 64, so we'll approximate it to 100, right? That will solve a lot of trouble. So we'll approximate, this is coming out to be around 6, you can say 6.28 is the value, right? So So now this will come out to be, so this is 32 pi squared plus yeah, 32 pi squared plus 128 pi into j. So if I calculate this will coming out to be, so pi square is around 10, so this will come out to be around 3.2, sorry, there's a minus, yeah, no, just a second, there will be a plus sign, sorry, not minus sign. So there will be 3.2 plus, this will come out to be around 128 into pi. So 128 into pi is 400. 400 divided by 100 is 4, so that will come out to be 4j. So answer should be around 3.2 plus 4j. I reiterate, I have assumed 2 pi to be approximately 6. The denominator becomes 100. So, but this is the approximate value that we are getting. So 3.2 plus 4j. Okay. I have to, so this will be slightly larger, so answer should be slightly less than 3.2 actually. So this will be the more correct option. Essentially you can put the values in the calculator and you can get the answer, but I just try to arrive at a more approximate answer. So C will be the answer that you will get. Again, the approach here that I was trying to say is that you can convert it in ZR and ZL, and you can apply all the analysis that we had talked about blindly. But just remember, these are complex numbers, so you have to also take into account the iota and other stuff. Okay, so we are right on time. I'm finished for this session. Just to summarize, we had talked about the Thevenin and Norton equivalence, a couple of questions on superposition, and then one question on how nodal analysis and Thevenin and Norton analysis can be interchangeably used depending on your comfort and the application of how the problem is designed. And finally we talked about phasors, that how phasors are important in when we are talking about sinusoidally varying signals, and you can just eliminate the sinusoid component and just talk about as if even in frequency domain we can directly apply all the nodal analysis, the Thevenin and Norton equivalence that we had talked about. We can directly apply them and we can solve this problem. So right now, for instance, we have just, it's a very simple problem, ZR and ZL, but you can, even if there is a complex circuit involved there with multiple voltage and current sources, you can apply superposition and Thevenin Norton equivalent. Everything else will remain as it is. The application will remain as it is, just the format will change, and that's all you have to worry about. So that's all from me. Thank you for your time and your patience. I'll stay here for a bit. If you have any doubts, any comments, any questions, please feel free to ask. In the meantime, I'll plug in my email address and my YouTube channel link again. So if you want to revisit, or you can refer to your friends. Someone was talking about some people who are unable to join, and if you have any queries, you can email me on the address that I have shared. So that is all from my side. If you have any doubts, any comments, any questions, I'll share a nice username, Fruity Rainy. I'll share I'll upload the video, and you can visit in a few hours. It will be uploaded. If not today, then definitely tomorrow. I'll try to do it as soon as possible. Yeah, that's it. Any comments, any questions on phasors, Thevenin, Norton, or nodal analysis, and anything? I'll stay around. Feel free to ask. Just hold on. Yeah, so that is it, I guess, from my side. If people want to leave, you are free to leave. You are free to leave earlier also, but you're welcome. Thank you for your time.
Thank you, sir.
I hope to see you again next week again, Saturday 6 to 8 p.m. That is my time. And by the way, other people are also taking sessions. So I think there's a session on Saturday, Sunday, Monday, and Tuesday, if I'm not mistaken. So you are encouraged to just visit the channel, visit their attend their sessions and see which one suits your style. So that's my suggestion. Thank you for your time. Good night. I'll be disconnecting the call in a few moments, but I'll wait if 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 other people have to talk. But you're free to leave. Thank you for your time.
Thank you, sir.
Yeah, welcome. Sanjay, Pavitra, Smita, and Navyata. Okay, Sanjay, Pavitra, and Navyata. Uh, if you have doubts, you can ask. Otherwise, I'll be disconnecting the call in a few moments. All right. Thank you for your time. See you next week. Goodbye.